Hi, my name's Jamie Linsdell. I'm from Cohere, and I'm really excited to be talking to you today about building generative AI solutions with Cohere and Elastic. Today, I'm going to cover an introduction to Cohere. We'll talk through our offering and what we provide on our platform. We'll talk through how we used Elastic to build our own internal AI assistant, and then we'll talk through the future of Elastic and Cohere integrations. To provide a brief background on myself, I joined Cohere about 2 years ago. I'm on the product strategy team at Cohere, and most of my work has been focused on our embeddings and retrieval augmented generation offerings. So what is Cohere? Cohere is the enterprise partner for large language models. What does that actually mean? Let me first give you a brief background on the company. So we were founded in 2019. We now have over 300 employees in 4 offices across the globe. We've got a number of really excellent enterprise partners, namely the major cloud providers, OCI, AWS, GCP, and Azure. And we've got a number of really exciting enterprise customers. We provide large language models for enterprise customers. We train these models ourselves and provide them through our platform. We train both generative models, which are the ones that people are familiar with through applications like ChatGPT, as well as embedding models, which take text and compute vector representations, which can be used for downstream tasks like semantic search or text classification. There's one use case in particular where these two types of models work really well together, and that's retrieval augmented generation. We'll talk a little bit more about that later on. But that's the process of retrieving information from some knowledge base or corpus and providing that information to a generative model to provide a grounded generation in factual, up-to-date information. So Cohere trains and provides access to these two types of models. What does it mean, though, for us to be focused on enterprise customers and be training these models for them? I think there's 3 things to think about, and this is sort of what we think about at Cohere. First is a focus on enterprise use cases. So as we're training these models, we're focusing on making them really good at the use cases that our enterprise customers care about and use cases that actually provide business value to them. So our models are really good for bringing into production for those types of use cases. Second, we support usage at scale. This has 2 components. One is cost, so our models are affordable to use at scale for very high volume use cases. And second, they're fast and have high throughput, so you can handle those use cases with fewer model instances. And then third, we're deployable anywhere. Cohere is cloud provider agnostic, and we can deploy our models wherever our customers need them to be. And those 3 things really make us the enterprise partner for large language models. So I mentioned our generative and embedding models. We're starting to see these 2 types of large language models be increasingly used in broader, more complex systems. And we'll talk about how our 3 models and the associated endpoints with those models are used to build more complex systems. So first, I'll talk you through our embed and re-rank models and endpoints. Starting with our embed endpoint, this provides access to our embedding models. And what this endpoint does is accepts some text as an input and returns a text embedding as an output, which can be used for downstream tasks, with the most prominent task being semantic search. Our embedding model has top performance on academic benchmarks, namely the MTEB leaderboard, and we have native compression available for our embeddings through our API. We provide int8 or byte compression as well as binary compression, and this allows you to retain nearly the same level of search performance, but reduce your storage costs significantly. We also have trained our embedding models to support use cases of 100 billion plus embeddings. Part of that is from being able to compress our embeddings effectively, retaining search performance, but reducing the storage costs associated with a corpus that large. And then second is we provide an embed jobs API, which allows our users to asynchronously compute embeddings for very large corpuses of text, which normally would take a very long time or be a hassle to set up. So we make that really easy to do. And then second or last, we're compatible with over 100 languages. We have a multilingual embedding model specifically. So we have an English and a multilingual model, and the multilingual model is compatible with over 100 languages and can perform cross-lingual search. And what you'll see with all of our models is that they're available across platforms. So our embeddings can be accessed on OCI, GCP, AWS, and Azure. Our re-rank model, available through our re-rank endpoint, provides a low-lift, last-mile improvement to search results by reordering them based on their semantic similarity to a query. This is different than embedding models. Embedding models take text in, so your query and document text, separately and compute embeddings, which you then compute the similarity of using something like cosine similarity. Our re-rank model takes the query and document text and looks at it at the same time and computes a relevance score. What this means is that you get a more precise relevance score from the model, but it needs to be run at query time because it's looking at the query and the document that was retrieved together. It adds a little bit more latency to your overall search system because you're adding this extra inference, but it increases the precision and the overall accuracy of the system, which is really helpful for RAG use cases. Some of the advantages of our re-rank endpoint: it's very easy to implement. It only takes a few lines of code. You would retrieve information from your Elasticsearch index and just pass those documents directly into the re-rank API and get your results back. There is a minimal impact to latency, so it does add some, but it's on the order of tens to maybe 100 milliseconds of latency. We also allow the ability to customize a re-rank model, so you can fine-tune that using examples of query document pairs that you know are good results. So you can fine-tune the model specifically for your use case. And then we also have a multilingual re-rank model, which is compatible with 14 different languages. So these two models and endpoints are used in combination to build state-of-the-art semantic search systems. But how does that tie into RAG? We have a chat API, and this is the primary way that our customers are building RAG-enabled conversational applications. Our chat API gives our developers access to our generative models and has a number of features that support the development of RAG-enabled conversational applications. And there's three that I want to call out. The first is query expansion. So the case that you would use query expansion is if you say, have a conversation that's happening between a user and a chatbot, and you're a few conversation turns in, the user might be asking a question or making a comment about messages that were stated previously in the conversation. And a very simple example of this would be the user is using some sort of pronoun that's referring to something in a previous message. On its own, that query might be underspecified. So if you were to just search with that, it might yield no useful results because it doesn't have enough information. You can use a language model to reformulate that query given the context of what's previously been spoken about in the conversation to get a more precise search query, which would then lead to more relevant search results. So we have a parameter in our chat API that allows you to just do query reformulation for that step in your RAG system. The second feature is document grounding. So this is sort of the most obvious feature. We have a parameter in our API that allows you to pass in a list of documents, and we will automatically inject the text from these documents into the prompt to the generative model in order to do a grounded generation. And so you can imagine you query your Elasticsearch index, you take those documents and pass them into the documents parameter, and we automatically handle the prompt engineering for you to get a grounded generation. The third feature is citations, and this is one that's really popular with our enterprise customers. We've trained our model in such a way that it can generate inline citations for the claims that it's making in its generation. So what that means is if you're providing the model with some set of documents from which you want the model to draw from as it's responding to a user's question, the model can also cite, as it's generating a response, which document it's pulling information from to generate a certain claim. And that allows users of the RAG system to have more trust in the response. They can actually click into a cited claim and see where the actual information came from. And it also makes the model more faithful to the content and generally increases the reliability. So that's something that our enterprise customers really like when they're building RAG systems. Finally, we have the ability to fine-tune a model for chat as well, so you can customize it specifically to your use case. So that's a little bit about the Cohere platform and the models that we offer. I want to now talk through how we used Elastic to build our own AI assistant called Pearl. So what is Pearl? Pearl is our internal workplace assistant. And so it's a chatbot that allows for retrieval augmented generation on our internal data. Why did we build this? Well, for one, we wanted to dog food this use case. We had a lot of interest from enterprise customers on the ability to do RAG on their own internal documents. And so we wanted to be able to try this out ourselves, learn from usage and feedback from our own employees so that we could bring those learnings to our customers and help them better implement these systems. And second is we actually wanted to reap the productivity benefits ourselves from having a system like this in place internally. So what are the main use cases for Pearl? We've now been using it for around 6 months, and 4 main use cases have appeared. The first is onboarding. So Cohere is growing quite quickly, and we have a lot of new employees. There's a lot of chaos in the company. It's a startup. And so it's really important that we support our new employees as they ramp up, and Pearl has been really helpful for that. Rather than having to tap someone on the shoulder or ping them on Slack, it's really easy for them to just ask simple questions about the company as they're onboarding and have them answered by Pearl. The second point is sort of replacing activity in our Ask people, Ask IT channels. And so people can much more easily ask questions related to HR related issues, expense policies, IT policies, etc., rather than having to actually ping our teams directly over Slack. And so that's been a really big time saver for our people team and IT teams. The third use case is developer questions. So this is mainly for our engineers being able to ask troubleshooting questions related to our tech stack at Cohere. And then the last piece is ongoing projects. So like I said, there's a lot going on at Cohere. And so it's really helpful for people at the company to be able to ask questions about ongoing projects that they might not be totally privy to, and have Pearl be able to keep them up to date on what's going on. So why do we choose Elastic for this use case? Well, there's 4 main reasons. The first is connectors. So Elastic supported the key connectors that we needed for Pearl out of the box and offered role-based access control. So we didn't have to worry about people seeing documents or messages that they weren't supposed to. The second is that Elastic provided the perfect level of abstraction for us. So Elastic provides the search infrastructure with the connectors and the ability to use our own models, but doesn't have, it wasn't a full point solution that we needed to implement. We were able to just have the search index running in our own infrastructure, and then use the connectors. And the reason that was important is we had our own user interface that we wanted to use, and I'll show you that in our demo in a second. The third reason is flexibility. And this is sort of related to the abstraction piece. We obviously had the ability to extend our usage of Elastic beyond the original use case of Pearl. And we've actually begun to use Elastic for some other internal use cases beyond just this enterprise search use case. And then lastly, support. We received really great support from the Elastic team when we were evaluating the product and doing implementation, and with any of the maintenance issues that we've had. Rebecca, Sid, Matt, Greg, Hemant, and others were super helpful throughout the process. So it's been great to work with the Elastic team. So I'll show you a quick demo of Pearl, just so you can better understand both our internal use case with Elastic, as well as how some of the different endpoints that I described work together to build a RAG system. All right, so this is our interface for Coral. This is just our standard chatbot. Anyone can view this online, coral.cohere.com. In my case, because I'm in the Cohere org, in grounding, which is where normally for external users, you might just see web search or any of the other connectors that you've built or added. I also have our Perl connectors here. And so I have them turned on. And what I'm going to do is ask, what is Perl? And so you can see that we're pinging these connectors, our Slack, Notion, and Google Drive connector. We're asking, what is Perl? This is where you might have the model reformulate the query. In this case, this was a well-specified query. The model didn't actually have to do anything. And then you can see the grounded generation. So Perl is an internal code name for Cohere's chat plus RAG. And if I wanted to validate any of these claims, I could really easily click in and sort of see which source this was coming from. And so in some cases, it's a Google Drive document. In some cases, it's a Notion page or Slack. And so these are the citations, the inline citations that I was referring to before. All right, so what does our actual Elastic infrastructure look like for this use case? So we're using self-managed Elastic in our own GKE cluster. This functionality would have been fully available through Elastic Cloud. Just for some internal policies, we chose to do it as a self-managed option. And that was really easy for us to set up and run. We're using Elasticsearch Enterprise Search with the pre-built connectors for Slack and Google Drive. For Notion, we actually built our own connector. Notion doesn't expose a search API that can sort of effectively be used to index the content into Elastic. So we had to build sort of a workaround for that. But I think that speaks to the abstraction and the flexibility of Elastic, where we were actually able to build this connector ourselves and ingest our company's Notion data into our Elasticsearch index without being sort of blocked by product decisions on the Elastic side. So that was great. And we were talking with the Elastic team about how we could do that. And so how does this actually end up working in production with enterprise customers? So this is a case study of one company that we worked with. So in their case, they were building a workplace assistant for journalists. The company was a large European media company, and they wanted to be able to provide access to a chatbot that could reference their 20-year archive of articles and allow their journalists to be able to ask questions about these articles, use it for research, allow it to help them write articles. And their stack was using Elastic as the search index, using re-rank to help with the precision of the search results, and then our chat API. Why did they choose Elastic? Well, they were already a customer for another use case. And in this case, their archive of articles was actually already indexed in Elastic. So that was really easy for them to get started with. Elastic also is really good for scaling up these indices. And so in their case, 20-year archive of articles was quite large. And so it was really easy to scale that up with Elastic. And then the last point is recency boosting. So in the case of this customer, it wasn't just enough to have semantic relevance for the content that they were retrieving. They also wanted to be able to boost more recent articles because those generally were more important for their journalists. And so that's really easy to do with Elastic and plays into the strength of their traditional search solution. Why did this company want to use Cohere? Well, for one, we have really strong performance on RAG. Our model is trained specifically for retrieval augmented generation, among other enterprise use cases. And we have some of the really helpful features for development that I mentioned earlier in our chat API, like query generation, documents, and citations. All right. So what is the future of Elastic and Cohere integrations? Well, we're really excited to announce that Cohere embeddings are now available through the Inference API. This was released in 8.13, and that includes access to int8 or byte compression via the Inference API. So you can access the native compression that we provide through our API via the Elastic Inference API. And that's great because it'll reduce the storage space of your embeddings in your search index. You can then, once you've set up your index with Cohere embeddings, use our re-rank API. Right now, this is just separate, but it's very easy to set up a query your Elasticsearch index, pass the results into the re-rank API. And then you can feed those results once they've been ranked into our chat API to very easily perform RAG. So this is just sort of the start, but we're really excited to be working with Elastic closely, and there will surely be more exciting announcements to come. So given that we have these integrations, why would you choose Cohere embeddings? If you take a look at this chart, on the x-axis, we have the cost to host Wikipedia. So basically, if you were to take a data set roughly the size of Wikipedia, say around 250 million embeddings, and you were to compute embeddings and have to host that, this is sort of an estimate of how much that would cost based on the size of the embeddings that you're using. On the y-axis, you have the MTEB average. So this is the essentially average accuracy of the embedding model on an academic data set. And what you see is that Cohere's models in orange have the best cost to performance trade-off. So the orange dot on the right is our embed English v3 model. So that's our sort of standard flagship embedding model. The dot to the left, which you'll see has almost no decline in MTEB average accuracy, is our embed English v3 with int8 or byte compression. And so this is the compression that would be available in Elastic. So what you'll see is you get around 4 times better storage costs, but you have almost no degradation in performance. And so Cohere embeddings allow you to have the best performance at the lowest cost. Why would you use re-rank? There's a few reasons. One, it's very easy to implement. It's literally one API call to get a new ranking of your documents based on their semantic relevance. It's very well suited for RAG. It works well with these conversational user queries that you tend to get in conversational RAG systems. It's retrieval agnostic, so it can be added to a BM25 keyword-based search index, a dense vector semantic search index, or a hybrid search index. And in fact, it's a really great way to sort of combine results if you're querying, if you're making 2 separate queries using BM25 or dense vectors. And then lastly, cost and latency is low, especially when you compare it against LLM-based re-rankers. So in some cases, people are using generative models to handle semantic re-ranking of documents. Re-rank allows for essentially comparable precision to the state-of-the-art generative models for ranking, but at 1/100th of the cost and significantly lower latency. So those are some of the reasons to think about adding re-rank into your RAG system to boost performance. All right, so how can you get started today? Well, I mentioned you can access Cohere's models through any of the platforms that you see here on this slide, including our own SaaS platform, which is probably the easiest way for you to get started. We would recommend going to our website and grabbing a trial key on our platform to get started with testing today. And then you can go on Elastic site and create a trial for Elastic Cloud or contact a sales rep in order to get started with their product for your vector DB. What would you get started with? Well, we've got a number of popular use cases listed on this slide here. But for us, when we think about use cases with Elastic, it's really semantic search and retrieval augmented generation. These are some of the more popular, more specific use cases. But really, the world's your oyster when it comes to building with LLMs, building RAG systems. All right. Well, it's great giving you an overview of Cohere, the work that we've done with Elastic, and the integrations that we have. If you have any questions, please feel free to email me, jamie@cohere.com, or contact anyone else from the Cohere team. Thanks for watching.